All right, today we're going deep, I mean really deep, into the cosmos to solve a fascinating mystery. We're looking at an ancient city of stars called Messier 107. And guess what? Deep inside it, we've picked up a pulse. And I'm not talking about just one heartbeat. We're hearing the rhythm of hundreds of thousands of stars. And here's the kicker. Some of them are starting to change their beat.
I mean, think about that for a second. How do you check a star's vitals when it's 20,000 light years away? It sounds completely impossible, right? But believe it or not, astronomers are doing it. And what they're finding in Messier 107? Well, it's giving us this incredible peek into the lives and maybe even the futures of these super ancient stars.
Okay, let's set the scene. Our subject, or maybe we should say our cosmic crime scene, is Messier 107. You'll find it about 20,000 light-years from us, hanging out in the constellation Ophiuchus. Now, this isn't just some random smattering of stars. Oh no, it's a very specific kind of stellar metropolis, and it holds all the clues we need.
So, what is it exactly? M107 is what we call a globular cluster. And you can picture it like a giant, spherical, tightly packed city made of hundreds of thousands of really, really old stars. The important thing to know is that they were all born around the same time, billions of years ago. And that right there is crucial. It means they're all cosmic siblings at about the same stage in life. So, when one of them starts acting differently, well, that's a huge deal. Okay, so our first clue is all about figuring out this cluster's identity. And to do that, we need to understand something called the Oosterhoff classification. It's basically how astronomers figure out the personality of a globular cluster. Yeah, so this whole system basically sorts clusters into two main groups, type I and type 2, and it all comes down to the rhythm of certain stars inside them. You've got your type I clusters, where the stars have a faster pulse, think about 0.55 days, and they're richer in heavy elements. Then you have type 2, where the stars pulse more slowly, around 0.65 days, and they have fewer heavy elements. It's kind of like the cluster's signature beat. So the big question is, which one is M107? Well, the evidence is overwhelming. Its stars have an average pulse period of about half a day, and its stellar population looks exactly like what you'd expect. All signs point to one thing. M107 is a classic, textbook Oosterhoff type I cluster. This is our first big clue, our baseline. It tells us what normal should look like for this place. All right, we've got the cluster's ID. Now it's time to zoom in on our key witnesses, the pulsating stars themselves. These are the stars that are going to spill the secrets. We're talking about a special kind of star called an RR Lyrae. Now these things are just incredible. They're variable stars, which means they literally expand and contract, getting brighter and dimmer with this amazing clockwork regularity. For what we're doing, it's perfect to think of it as a stellar heartbeat. And guess what? We know how to listen to it. So how do we actually do that from so far away? We create what's called a light curve. And honestly, it's basically an EKG for a star. No joke. It charts the star's brightness over time so you can see the pulse. The brightness goes up, it comes down, up, down. By measuring the time between those peaks of brightness, we can nail down the period of its heartbeat with just stunning precision. But here's the thing. A single EKG just gives you a snapshot in time, right? To see if that heartbeat is actually changing, you need to watch it for a while, a long while. And that brings us to our third and most powerful piece of evidence, an 82-year-long surveillance. Look, the key thing to get here is that stars evolve on just mind-bogglingly slow timescales. We're talking millions, even billions of years. So to actually catch a star in the act of changing, you can't just pop out with your telescope for a few nights. Nope. You need decades of incredibly patient, careful observation. And that is exactly what astronomers did. This wasn't just one team's project. This was a multi-generational effort. Think about this. It started back in 1935 with old-school photographic plates. Then it was picked up again in the 70s and again in the 90s. And it all wrapped up with modern digital cameras in 2017. That's an 82-year-long watch. Just incredible. So after all that work, after combing through 82 years of data on 22 of these stars, the verdict came in. And it was crystal clear. The vast majority, 82% of them, had heartbeats as steady as a metronome, unchanged for almost a century. But, and this is the exciting part, 18% of them were different. 4 stars. Their pulse was changing. Okay, this is it. This is where we solve the case. We've got our motive, it's stellar evolution. We've got our evidence, those 4 stars with changing pulses. Now all we have to do is read the EKG. So what does it actually mean when a star's pulse starts to change after billions of years of being steady? It's a huge deal. A stable pulse means the star is just chilling out in a long, quiet phase of its life. But a changing pulse, whoa, that means the star is actively evolving. It's changing, right now, on a fundamental level. And the amazing thing is, we can read these stellar EKGs and know exactly what's happening. It's pretty straightforward. If the pulse is speeding up, that is, the period is getting shorter, the star is on its way to becoming hotter and bluer. If the pulse is slowing down, the period is getting longer, it's evolving to become cooler and redder. It's like we're watching its life story unfold in real time. So when we apply this to our patients in M107, we get a really clear diagnosis. Those 18 stable stars, they're just cruising, evolving super slowly. But our 4 stars of interest, well, 3 of them, V10, V12, and V16, have speeding pulses. They're evolving toward the blue, getting hotter, and the last one, V17, has a slowing pulse. It's headed the other way, toward the red, getting cooler. The researchers put it perfectly. Period changes are a consequence of stellar evolution. I mean, let that sink in. What we're seeing here isn't just some random flicker or statistical noise. We are literally watching the direct result of stars evolving. We're watching them age right before our eyes. But hold on, because there's a really cool twist here. Those 3 stars with speeding up pulses, they're changing so fast that astronomers think they might not be old stars slowly aging. Instead, they could be what we call presaged stars. Basically, stellar newborns just settling onto the main stage of their lives. So we could be seeing both aging and birth. And just when you think you've got the case all wrapped up, M107 throws another curveball at us. Take a look at this light curve for a star called V7. See all that scatter? The pulse isn't just changing its speed. The whole shape and strength of the pulse is varying wildly. In medical terms, this is a stellar arrhythmia. This weird behavior has a name. It's called the Blazhko effect. It makes the amplitude, the strength of the star's pulse, get stronger and weaker over time. And what's wild is that this is a totally separate mystery from the slow evolutionary changes we were just talking about. And honestly, scientists still don't fully understand why it happens.
So what's the big takeaway here? By putting our cosmic stethoscope up to Messier 107, we've learned that these ancient cities of stars are anything but static museum pieces. They are dynamic, living, breathing laboratories where we get to see the laws of stellar evolution playing out for real. This 82-year-long stakeout of M107 has given us stories of change, of stars aging, maybe even of stars being born, and these totally baffling arrhythmias. It just goes to show you that even the most ancient parts of our universe are still packed with secrets. And it really makes you wonder, doesn't it? What other secrets are we going to uncover in the next century of watching the skies?